Hello, everyone. This is Professor Tina Burns, and I am here again for your summer session of computer architecture. This is actually the final lecture. You guys will have your final exam after this lecture. But today, we're going to go over lecture 7. We'll talk a little bit about assembly language and how that relates to your processor and how that all kind of fits into our C code and what we've been doing. All right. So um, let's go ahead and get started. I'm going to go ahead and share my screen. All right. So um, as we kind of look at this and we review it, uh, as I stated before, this is in fact lecture 7. So just give me 1 minute while I increase the size of, oh, there we go. Increase the size of this. Okay. So here's what we're going to talk about today. We're going to review the computer architecture model. Now, this goes back into the first 2 lectures. We talked about why are we learning computer architecture? What does C have to do with it? Why are we choosing C? And how does that all relate to us being better programmers and also just in general learning how to interface with our different hardware within a computer. So this is all going to tie into what we're talking about today as we go into more detail. As we go into more detail about assembly language and C code and all of that. We're going to talk about storage and memory. Now, keep in mind that we talked about the PPM for computer architecture. Power, right? Because if you don't have any power, you can't do anything. You have to have the unit on. How can I optimize my power or minimize what is required to operate my components in my computer? The more I minimize the juice that is being sucked out, the longer my computer will last, the more efficient my programs will be, and just the better operations it'll have. Power processing, right? That was their second P, where is how fast is my CPU? How many things can it handle at once? How many cores does it have? How much can it handle in terms of video processing? What's the speed of it and what's the efficiency of it, right? Power processing. Processing is going to be extremely important, especially as we gain more and more information, as we work with large language models, as we do AI, the ability to be able to effectively process that rapidly is essential, right? And then memory. Memory is kind of like and we'll see that in this lecture. It is it's like the breeding ground for everything. We have to read and write from memory. Everything that we get, even our commands, even how the processor is working, is pulling that from memory, right? So what we want to talk about today is how do we optimize that, how we optimize our programs so that it can effectively pull and get the information from memory. So we have our power, we have our processing, and we have our memory. So we'll talk about storage and memory and how that relates to our C code and also how that relates to assembly language. We're going to talk about control flow a little bit as well, because as we send out our commands, we're doing that in sort of a flow of information, right? If I say I'm running a for loop where I want to increment a counter every 10 seconds so that I know how long it takes me to do something, that has a flow. So I want to say, okay, read this. I'm going to set this value initially. Then I'm going to go ahead, wait 10 seconds, and then I'm going to increment it. Then I'm going to jump back to that first command where either I set the value or I read it. That is sort of how a control flow, and it dictates the order of operations that we're going to do in a program. And we'll talk about this a little bit later. We're also going to talk about assembly language. I know some of you guys were looking forward to that. And unfortunately, we got to this a little bit later than I expected, but I'll try to at least give you guys the basics of it and kind of how that relates to what we were talking about earlier. And then we're going to talk about how we can kind of optimize that. What do we do? How can we, and see, is there a way to implement that so that we can optimize our C code a little bit? All right, so let's start from the beginning. Let's start from where we started in lecture 1. I think this was lecture 1 or lecture 2. Either way, you'll remember this model. This is a model that represents the data flow or data instructions flow for computer architecture. This is one of a few models, right? But this is the one that we is kind of common, and it's a very easy model to follow as we're thinking about kind of the way that we're flowing through this particular through these particular items. So I'm going to see if I can. There we go. Okay, so if we look at this, here's our memory. Our memory is this big honking thing, right? And we're talking about RAM memory here, where we have a bunch of things talking to it. We have the control unit that is dictating, okay, how much, when can I write to this memory? When can I read from this memory? We have the processing unit that is handling information, it's handling details, and then it's receiving stuff from memory, and it's also writing to it. And then we have we'll talk about that a little later on, but we also have our program, our executable that's accessing this memory. So this memory is a huge portion of our programming. It's a huge portion of the functionality of the for this process overall. All right, we have our control unit and then our processing unit. And then of course we have our input and our output. These are the peripherals and everything that allows us as users to interact with this information, right? We can't directly say, okay, I'm gonna pull this from memory, but we can send a command through our keyboard, through our sometimes through your monitor if it has touchscreen to do a particular item or operate and have a particular function, right? So that's our basic flow of information. Now we're going to talk and go a little bit more to detail with how that works as we go from the upper level to the lower level. Now keep in mind, this is the basic structure for us, right? You're taking memory, you're accessing information from memory. You start from the bottom up, excuse me. You have your input and your output, right? This is what we see as users, right? And then that information is kind of handled, like the central processing unit is going to be talking back and forth between these two. And then all of this at the bottom of that, our foundation is going to be the memory unit. That's going to be where the foundation of the instructions and the data is held. So let's talk a little bit about, give me 1 minute. Let's think about that a little bit more in detail, right? We talked about how, yes, it's super, super important to understand these aspects of memory. It's super, super important to understand the processor. Now I want to talk about, I want to go over a little bit with, excuse me for a minute. I want to go a little bit over how all this kind of fits in to the memory and look at that in storage and a smaller scale. We have our main memory, right? That's really kind of this block that you see here. The main memory or the RAM, that's where you're allowing all these processes to kind of be stored and where you're sending the information back and forth. That's why when you have the more RAM you have, the more processes you're able to handle and the quicker you can access stuff, right? So we have our RAM memory, which is a large memory set in comparison to what we're talking about here. It's this large memory set. And you see how it's at the base of the structure here, right? This is kind of at the bottom of the structure. From here to here, you really got to go through a couple things before you can access this memory, right? It's a large memory set. It has a lot of room compared to our other registers and storage, but it takes a little while to access it. And it stores a bulk of the programming information. Our memory is going to have both it's going to have our instructions, and it's also going to have the data. Now, we talked about this, right? The whole lecture 6 was talking about, all right, I know it takes me a little while to access a memory, right? Imagine you have, I don't know, 2,000 addresses, 2,048 addresses, let's say, right? And I want to access something that's at address 1,155, right? I have to go through all that stuff and this big honking thing to access it, right? So we said, okay, is there a way to cut down on that time? And that's why we went to cache. Now, keep in mind, memory is it's a big chunk of information. It's a big space, right? Caches are this thing between, right? It's between your main memory and whatever you're processing that allows you to store a small subset of that data, which gives you quick access to the information. And it's also close to the RAM so that I can quickly access the information and send it back to my program. And typically what you're going to have in this is information that is accessed frequently, right? If I'm in a loop and I say, I want to keep on incrementing this counter, you're going to store it there so that I can access it quickly and I don't always have to go back to main memory. That's my RAM. Now, what we have not talked about in detail is registers. All right, so let's go back to that von Neumann model. We have this memory that's at the block, that's at the base of what we're doing. And then we have our central processing unit, which is kind of in between that, in between the memory and what the users have access to, right? So in that, there's a storage component, right? Where the memory, the RAM memory stores your data and your instructions. There's also secondary storage. There's a storage that's connected to the CPU that allows you to store information in registers. Now, registers are also a small memory set, and they allow fast access to information and allows you to access the commands and different things from the CPU. This has quick data access as well. So to review, if we look at the cache and we look at the registers, both of them are quick data access. They allow you to get information quickly. The cache is going to be associated with getting quick access to the RAM memory. And the registers are going to be associated with getting quick access to the CPU. Now, the CPU is what handles the instructions. It's what does the work. The memory, the RAM stores the information, whereas the CPU processes it. It does the work and all the details, right? So if I can access these registers quickly, then I can access the ability to handle and process these commands a little bit more quickly. And both of these, when we look at them and we compare them to the main memory, are a much smaller size. And that is because we want to be able to have that fast and quick access to whatever functions we desire to do. Now, as we talked about, right, we went into discussing the CPU and how we want to use that. And we have these instructions that I'm giving, right? I'm going to say A is equal to 15. And every 15 seconds, I'm going to increment that by another 15. I'm going to keep on doing that. There's a control flow to how I want to do that. If I'm in a for loop, it's a control flow. I want to keep on doing this until something happens. And then I'm going to go back to the top of that for loop. Our control flow is really described as the order in which instructions execute, right? So typically if we're in a C program, right, that's going to operate from top to bottom. That means I'm going to execute A, B, C, D, E, F, or instruction 1, 2, 3, 4, etc. Unless I interrupt that control flow with some sort of instruction, right? So if statements allow me to interrupt that flow. It says, okay, if I say A is equal to 4, B is equal to 8, and C is equal to 9, right? I have 3 things that I'm executing that I'm giving explicit instructions for. But what if I said I only want C to be equal to 9 if the user sends a command, right? Then I interrupt that storage of my C component by adding an if statement. Another way to interrupt or change that control flow is through for and while loops, right? Instead of me going from top to bottom, I can put this loop in that allows me to change the flow. Instead of having a linear flow, it becomes more of a pattern or a cyclical flow. And you do that with these loops that allow us to adjust the control flow of our program. But from a processor's perspective, we need to know, how do we do that? How do we change that? And how do we really access that quickly? Now we know how to do that easily within our C program. We've written a bunch of stuff already that has for loops, while loops, if loops. We already know how to do that. But how does the processor handle that? And if I know how it handles it, can I make it handle it and do a little bit faster? The answer is yes. So as we look at how the processors handle information and as we look at the control flow, let's look at how that relates to our program, how we actually program stuff. The first thing we're going to do is we're going to write a C code. That's what we've been doing for the entire course, C code. All right, so that C code, remember, is a high level language. So if you remember from our previous class, we have high level language that's human readable. So we can understand that. That second stage, after we get to our high level language, right, is going to be the assembly language. All right. And then after we do that, we have our machine code. I actually don't like that. You know, I could have just written this as text. That's probably what I should have done. And it's fine. All right, so these are our three things that we're looking for. For high level language, right? That's going to be anything that you're writing in C, Python, Java, HTML. The processor does not understand that. So that's converted. That's usually when you do your executable, that's converted into binary. Now we have the assembly language, right? This is what we're going to be talking about today, this assembly language here. That's a intermediate between your machine code, which is a bunch of zeros and ones, and your high level language that says X is equal to 3. There's an intermediary between these that still allows us to access this information. And keep in mind that this is what the user sees. And this is what the processor sees. Right? So we have this this data flow. We write a program in C using our C code. That's compiled. C code is the high level language that's compiled to an executable. The executable allows this to be written or is done, is completed. It is processed and it can talk to the memory and all that in binary. So we compile it, we get it to an executable so that my processor and everything can understand it. And then the executable can read and write to the memory. That's where all the information is stored. So remember I said the memory is it's the foundation for a lot of the information. So this memory holds allows the executable to communicate with it. It holds all our data. The executable says, hey, here are the instructions. It's going to give that information to here. And then it's also allows the executable to retrieve information from there. It allows it to say, okay, X is equal to 5. What's Y? You can get that, you pull that from memory. The memory then in turn is what allows us to communicate and get the information to the CPU. The CPU is what handles all the processes. If I say I want to add something, if I want to add these two variables, that's going to be done in the arithmetic logic unit that allows me to then take on and process this information. All right, so that's kind of the programming flow. If we look at it from the top level, from RC code onto how that is then interpreted or handled by the CPU. So let's look a little bit further into that control flow, right? And this is all going to make sense because remember, there's so many levels to this. There's you from a user, you're programming this from the outside. Then we have this CPU that we want to talk to and command, but there's also this block of memory that's in between it. And we have to figure out how to optimize and maximize that so that we can get these commands done quickly and so that we can retrieve that information quickly. So this is kind of an example of how this data flow looks, right? If we imagine I'm actually going to draw that. Our processor, our C code, or I'm actually going to say our EXE is here, right? Getting information, retrieving information from the memory. This is where EXE is. This is where we start so that we can get all the data. So say, hey, I want to do something, A is equal to 3, B is equal to 5. Give me Y, which is the sum of 3 and 5. All right, so it's going to give you all that information. It's going to talk to the memory. The memory says, okay, A is equal to 5. That's stored there. The processor then handles that. B is equal to 3, or whatever I said. I probably mixed those up, but either way, A is equal to something, B is equal to something. We take all that information in, and now the next one is an instruction. The instruction is add A to B. We send that instruction over to the processor. The processor takes that information and it says, okay, now what is A plus B? That data is stored back into memory. So that's the flow. Program, write to memory, given instructions. Memory, here's the data, here's the instructions, processor, handle your business. Processor, all right, I've taken care of the work, I've done my business, here's the information back to memory. Cool, I have the information, let me go ahead and send it back to executable. Executable says, all right, I'm fine, let me display that or give that to the user. That's the flow. And the faster we do this flow, the more rapidly we do this flow, the better. So before we jump into assembly language, we have this ability for the executable to talk to the memory. But what if there's a way to access some of these registers and things within the processor a little bit more rapidly? I can't necessarily do that from my main program, but I could essentially do the operations a lot more quickly if I knew the register, right? We talked about your memory is going to have specific addresses. Your processor is going to have registers that you can talk to specifically. Well, if you know where they are in the assembly language, you can actually communicate with them and pick them directly to make it a little bit easier. So your assembly language says, hey, I want to cut out a little bit of the middleman and make these processes a little bit quicker. In order to do that, we should understand what those commands are to the processor, right? Your processor says, do this, do X, do Y, do Z, store this here, do this, whatever the case may be. And it can handle it. It's a little bit more easy to interpret it from an assembly language. So here are our common instructions, right? These are the common instructions to some of the, to a lot of the, now keep in mind that each processor, the assembly language is going to be a little bit different. So it might look a little bit different in terms of how it's set up, but these are the basic functions, right? How they're implemented and executed. I shouldn't say how they're executed. How, like, the syntax of them might be a little bit different from processor to processor, but the basics of it is here, right? If I want to move something, right, I want to move data from one location to another. In assembly language, you would just write that as move, and then your two operands from where you want to move it from to. If you want to load and store information between memory and registers, these would be the functions that you use. Similarly, if you wanted to perform some sort of arithmetic operation like adding and subtracting, these would be the commands that you kind of use, and so on. For the jump, skipping to a particular thing, comparing two things, and of course the bitwise operators that you would use to handle certain commands, right? These are all kind of your assembly language instructions that you can use in that particular thing. So how do we do that? How do we, what does it, what does assembly language look like in comparison to our C code? Well, one very easy way to see that is you can actually compile it using GCC and the -s command, and that will actually allow you to see your C code in assembly language. It'll create this file with the .s extension. So if you save it as test.c, it's going to go ahead and store that as a like test.s, and that will have your assembly language version of your code. So let's go ahead and do that. Let's go ahead and do an example with that in there. Now, keep in mind, I am going to do this in my normal fashion with Notepad++ and um, Notepad++ in my WSL, but you can do it in whatever IDE you choose. This is just easier for me to work with. So let's go ahead and clear this. We're going to make a directory. Call this lecture 7. So you see it's empty. I just created this directory. The first thing we're going to do is we're going to go ahead and make a makefile, just so that I can compile my information, make sure it's there. I'm going to open it up here on this side. Actually, let me go ahead and open this one so I can copy this information over. All right, this is the one we're working with. You can see that's empty. I'm going to go ahead and copy it over and save it. We're going to create a new file, and we're going to save this as test.c. Okay, so now we have our test.c program. Of course, we know we're going to include our main, our libraries, include standard input output. We include I'm not sure I'm gonna need, I'm gonna put it in here. I don't know if I need the standard library, but I'm gonna include it. All right, and of course, we're gonna have our main function. We're gonna return exit success. This you guys already know. We're pretty familiar with that. And what I'm gonna do is print out to the screen assembly language tests. Let's test it up. So let's go ahead, let's make this. I always get that mixed up. Oh, that should be .h. All right, so now we got all those there. Let's go ahead and clear that. So now we have our thing. Let's go ahead and execute this. And it executes what we want to see, right? Now, if I wanted to take this, I'm actually going to add a couple of other things here. Right now, I just said, hey, I'm going to go ahead and test this out. I want to set this up as a program. Let's say I have A is equal to 5. B is equal to 3. And I want to go ahead and print these out to the screen. All right, we're gonna execute it here, and then we're also gonna look at how that looks in assembly language. B A is %D, and we'll make that A. Okay, we're gonna have that here as B is that, and we're gonna make this E. We can compile that without the errors. Oh, we need to set these up as integers. The problem is that I am really used to writing this to programming in Python, and I forget that I need to declare the variables types and see. Anyway, so we have that, and let's go ahead and execute that. And you'll see this is what outputs to the screen. Assembly line language test done. It's output to it, right? And let's look at what we have. We have these three files: our make file, our .c file, and our executable file. Now, let's go ahead and look at what this looks like in assembly language. So this is how we create an assembly language version of this file. .s, and then we're going to do test.c. It's going to create that. And if you look, you'll see this new file that's been generated here. Let's go ahead and open that up. Let's go ahead and open that up. Okay. So here is our C language version of that. I'm going to see if I can increase the size of this a little bit. All right. Here is what this looks like in assembly language. Now notice how what it starts off with is telling me and declaring what my file is, right? We called that test.c, that's the name of our file. Then it has kind of this section information. And then what it does is it stores these text values, right? I just say, okay, this is LC0, LC1, LC2, three separate identifiers for the text values is how it stores it. And then we have our, what it's doing right here is setting up your, whatever your global is for your main, right? So that is what it's doing for those initial functions, right? And then as we come down here, we see it doing a bunch of things and with a bunch of operations for our C program. But you'll notice some of the things we talked about in the slides, this move function, I'm taking this between these two, and that's where I'm moving it. These RBs and all of that are actually just pointers. We're pretty familiar with that, right? There's also pointers in assembly language. It just makes it easier for you to move and to access information and to move things back and forth. So we have this where it's doing all this information. And what happens here, remember, the two values that we wanted to store were A. We wanted to store the value of 5 into A. And we wanted to store the value of 3 into B. So what you'll see is happening here is that it takes this information and this puts plots. I believe it calls the function to plot it out to the screen. That's what I think is happening. And I think it's doing that from, yes, okay. So this LCL here is plotted or printed to the screen here. That's the assembly line function, so it's printed to screen. And then these pointers that I set up here, what that's actually doing is saying, okay, I'm going to store these two values, keep these as pointers, right? I'm going to access those two values. I'm going to keep those. And these are going to be kind of the registers I want to associate with them with. It's EAX. That's the register I want to associate with it. And I'm saying, hey, this is going to be here for 5. This is going to be here. I want to move these two items into this position of these registers. I want to move 5 into this position at -8, and 3 into the position at -5, really from at this value E of X, right? And then if you'll notice that second line, I said, I've stored these now in my assembly language. What I want to do is I actually want to print the value of A, right? And keep in mind, this is stored as an assembly language. This is stored as LC1. So this then calls that and says, hey, I want to take this information and the data that I had stored here, I actually want to include that. I want to include that in my directory, and then I want to print that out. So I'm going to store it here, and then I'm going to keep that. I'm going to input that here, and then I'm going to print that out. That's what this is saying. The next function is I have that, but now I want to go ahead. This was at register, this address here, but at locate register here, but at 8. Now I'm going to take the same thing and I want to do the same thing for B. So at -4, right, of this register, I'm going to go ahead, include that into this, and then output that to the screen. So that's the basics of how this is working. That's the basics of how this assembly language is working. And what you'll see is you'll notice that this is a lot more lines. This is a lot more lines of code than we would typically use in a regular C program to do all those functions. And then this footer, I believe, is standard. It's doing a bunch of other stuff that's required for the assembly language. So like this looks like it's telling you what kind of compiler you can use, or the compiler that was made for this, etc. But that's basically this move, this call. I'm saying I'm moving from one point to another. This call means I'm calling this print operation to get it from the screen. And you'll see it just has a lot of moving and different things here. So let's go ahead and update this and make this a little bit more interesting. What if we declared an integer C, and we said that integer C is equal to A plus B. And we want to go ahead and print this out to the screen. Let's see how that changes the assembly line code, and let's see how that changes the flow a little bit for how these are written, right? Do I have that right? Let's go ahead and make this guy. Let's go ahead and run this. Just make sure it runs out. Yep. And then we said A plus B. So we have that information there. And let's go ahead and recompile this as a C operator. I'm going to reload that. Okay, now you'll notice I have this new string stored here in LC3. And let's look at how it changed our operations. All right. We had A, B, and C before. We have 5 and 3. It changed a little bit of the location for where we're storing those values. If you remember before, they were at -8 and -4. So it changed it slightly. It's getting all of those information. It's getting that. It's storing this out here. It's going to output that. It's going to output this information for LC3. But notice how, as I'm trying to, excuse me, so we have a lot of the same functions here where it's storing the information, but you'll see now this add function, and that add function is what we are using to combine these two numbers. And we're storing that in a particular location. So it says, hey, I'm going to go ahead and I want to add these two, my ed of x and ea of x. So I have these two variables right here. And notice the format of this. Add one is my command, and then the two operands are here. I've stored this in this register, ed of x and a of x, and all I'm doing is I'm going and I'm adding it. And then I'm moving that to this so that I can access it. And this is going to be my pointer to that added number. This right here is my pointer to the number that we have just added. Then I go ahead and we do our print functions to screen. Here is where the interesting part is. Before I have this, now I have this that I want to access from where I've added, and I want to print that out. And this allows me to access that and then print it out to the screen. So that's kind of the basics of it. And as you work with more and more with these, if you can feel free to do this in your own time, you'll get a better understanding of kind of how these functions and different things flow. I'm gonna go ahead and minimize this. Let's go back to our slides. That's not it. So we've just demonstrated how you can kind of create this on your own. Very simple with the GCC command -s and then your file, and you saw how it stored it as a .s file. So if we look at this, you'll see kind of where that was stored. We went through that. And really can break these down into these three sections. This is kind of the header where it takes all of your text information and it stores it. Then this next function is where it was kind of doing most of the operations. And then the footer is additional like overhead information that's needed for the process in the file itself. So what if I wanted to implement a portion of this from C code? A might be asking, why would I want to do that? Like, who wants to do that? Well, one of the reasons you might want to do that is so that you can have quicker access to the registers, right? Imagine that you're able to, rather than waiting for it to be, handled in memory, it has to go to memory, then it has to go from memory to the processor, then the processor handles it, sends it back to memory, and then it sends it back to the executable. One of the ways you can reduce some of that is you can write it. If you know what register you want to write it to, go ahead and write commands right to the register. And here's an example. I did generate this with ChatGPT, but here's an example of how you can do that with a very simple code, right? If I were to write this, yeah, I guess we can go ahead and do that. We can go ahead and do it. We're going to execute this, but let me just explain it first. So if I wanted to do inline, they call it inline assembly language in C. The way you would do that is by including this ASM command. The ASM command will allow you to include a bunch of operations in assembly language. So you can write it like you're writing in assembly language, kind of, sort of. It's still a little bit higher level than a regular assembly language, but it will allow you quicker access to that. And if I did this, for example, what you'll see is that when this is executed, what it's going to do is it's going to summarize this. Like if I were to do this as a regular C program, this would be one line. I would just say the sum. All I'm doing right here is this right here is just saying sum. I don't want to do it this way. Let's do this as a text. This is just saying sum is equal to A plus B. That's what this is writing. This section of code, that's what this section of code is writing. But the benefit of this is that it's not writing it to memory necessarily. It's writing directly to the register. So this first line of code is telling me what I want to do. I want to add these to, right? That's my function, add these. And it's also telling directly the registers that I want to add and then where I want to store it, right? I want to move these to these particular registers. And if you remember, that's kind of what we have to do each time we store something. We have to kind of move it around so that we can access it more easily. But this is a little bit quicker because it allows me to directly talk to the registers, to directly include what those registers are, right? Then once I actually store it, I have the information, I can print that out. So that would be the basics of if you wanted to do kind of this inline command with using some of this assembly language right from your C compiler, right from your C code. So that is basically, oops, that is basically one way you can do it. Now, keep in mind that if you try to execute this or create this in C, depending on your compiler, it might not um, recognize it. It might not recognize the command, the assembly line command. So you have to do a little bit of work to determine what the compiler will recognize as this assembly language and what your processor will recognize as well. All right, so I'm gonna stop sharing my screen. And that's pretty much the basics for how you can kind of parse through and understand a little bit more about the assembly language. Um, and that's pretty much it. All right, guys. So enjoy the rest of your day.